Look around you right now. Whatever room you are in, whatever surface you are sitting or lying on, whatever objects surround you in this moment. The walls, the floor, the ceiling, the furniture, the device you are using to receive these words. All of it appears solid. All of it appears stable. All of it gives every sensory impression of being the kind of thing that will still be there tomorrow, next year, a century from now. Your brain processes your environment and files it under permanent, reliable, fixed, the background against which your temporary life plays out against something enduring. This feeling is one of the most consequential illusions in the history of human thought. Not wrong in a minor, pedantic, technically speaking kind of way. Wrong in the way that flat Earth was wrong. Wrong at the level of the most basic structural assumptions about the nature of physical reality. The permanence you perceive in the objects surrounding you is not a property of those objects. It is a property of your nervous system, which evolved to operate at scales of space and time where the underlying fragility of matter is completely invisible. Push that same matter to the scales where physics actually operates, zoom in to the level of atoms, zoom out to the level of galaxies, zoom forward to the timescales where cosmology lives, and the picture that emerges is not one of permanence interrupted by occasional fragility. It is one of fragility so total and so layered and so fundamental that the stability you experience is a statistical accident of extraordinary improbability. Maintained by conditions so specific and so contingent that their existence requires explanation. The terrifying truth about how fragile everything in the universe really is does not begin with asteroid impacts or stellar explosions or the heat death of the cosmos. It begins here, in the object you are most certain is real and solid and present. Your own body. You are approximately 7 octillion atoms, 7 followed by 27 zeros. Each of those atoms is almost entirely empty space. The nucleus of an atom, which contains virtually all of its mass, is roughly 100,000 times smaller than the atom itself. If you expanded a hydrogen atom to the size of a football stadium, the nucleus would be a single grain of sand at the center, and the single electron orbiting it would be somewhere in the upper bleachers. An invisible speck moving so fast that it smears into a probability cloud rather than a point. Everything between the grain of sand and the bleachers is nothing. Vacuum, a void so empty that it makes the space between stars look crowded. This is not a metaphor or an approximation. The atom is almost entirely empty space, and you are made of atoms. By volume, you are almost entirely nothing. Now consider what that means for the concept of solid. When your hand touches this device you are holding, you experience contact, pressure, resistance. The sensation of something solid meeting something else solid. Your nervous system reports physical contact and your brain files it as such. But at the atomic level, your hand and the object are not touching in any meaningful physical sense. The electrons on the outermost shells of the atoms on the surface of your skin are approaching the electrons on the outermost shells of the atoms on the surface of what you are holding, and the electromagnetic repulsion between those electrons is preventing them from getting any closer. Your hand is not touching anything. It is hovering at an electromagnetic boundary, held at bay by the same force that makes a magnet push away from another magnet when you orient them correctly. Every physical contact in the history of human experience has been this. Not solid matter pressing against solid matter. Electromagnetic fields resisting each other across the vanishingly small distances between the outermost electron shells of atoms that are themselves almost entirely empty space. When you shake someone's hand, when you sit in a chair, when you feel the ground beneath your feet, you are feeling the electromagnetic force doing its job of preventing things from occupying the same space at the same time. You are not touching the world. You are feeling the force that keeps it apart. This reframing of solid is not merely interesting. It is the first layer of a picture that becomes progressively more unsettling the further you follow it. Because if solid is an illusion maintained by electromagnetic repulsion, what maintains the electromagnetic force? What maintains the atoms themselves? What maintains the laws of physics that govern how atoms behave? And what maintains the fabric of space-time in which those laws operate? Each of these questions has an answer, and each answer reveals a deeper layer of fragility than the one before it. A structure not of solid foundations, but of contingent balances, each one depending on the others, each one operating within ranges that could in principle be otherwise, each one failing if the conditions that sustain it are disturbed beyond specific thresholds. There are 5 layers to this fragility. The first is atomic. The particles that make up matter, the protons and neutrons in every nucleus, are not guaranteed to be permanent. They can decay. Not on timescales relevant to human civilization, but decay is what the physics suggests, and permanence is not what the evidence supports. The second layer is the constants. The specific numerical values of the fundamental forces and masses and charges that make chemistry possible are not derived from any deeper theory. They are measured and accepted as given. And if they were even slightly different, not dramatically different, slightly different, the universe would be unrecognizable, incompatible with any complex structure, certainly incompatible with you. The third layer is the vacuum itself. The space you move through, the fabric of reality, may not be in its lowest energy state. It may be balanced in a configuration that could transition to something fundamentally different, with no warning and no survival for anything within it. The fourth layer is the cosmic forces. The expansion of the universe, driven by an energy whose nature remains unknown, is accelerating. The force that holds galaxies together is losing its contest with the force pulling everything apart. And the second law of thermodynamics guarantees that the endpoint of this contest is a universe of maximum disorder, minimum structure, and zero possibility of anything interesting ever happening again. The fifth layer is the one that sits beneath all the others. The assumption that the rules themselves are stable, that the laws of physics operating in our observable universe are the only possible laws, that there is no deeper level at which even this framework dissolves into something our current understanding cannot address. Each of these 5 layers will be examined in this video. Each one is real. Each one is grounded in physics that has been measured and tested and peer-reviewed, and in most cases confirmed to a precision that leaves little room for comfortable dismissal. These are not speculative nightmares invented to unsettle you. They are the conclusions that the most rigorous scientific investigation of physical reality has produced, stated as plainly as the evidence allows. But here is what this video is not. It is not a catalog of reasons for despair. It is not an argument that nothing matters because everything is temporary. It is not the cosmological equivalent of telling someone their houseplants will eventually die, and therefore they should not water them. The fragility of the universe is not a problem to be solved or a fact to be mourned. It is the mechanism, the engine, the specific structural feature of physical reality without which none of the complexity, none of the chemistry, none of the biology, none of the consciousness sitting somewhere right now receiving these words would exist at all. Stability is not the condition for interesting things to happen. Stability is the condition for nothing to happen. A universe in perfect thermodynamic equilibrium from its first moment would be a universe of uniform temperature, uniform density, no gradients, no flows of energy, no possibility of structure, no possibility of stars or planets or oceans or organisms. The fragility is not the failure mode of the universe. It is the operating mode. The place where everything that has ever existed and everything that will ever exist is possible. By the end of this video, the fragility will not feel like a threat. It will feel like the most remarkable fact about the universe. But to get there, you have to follow it through every layer. And the first layer, the one that sits closest to the surface of everyday experience while remaining almost entirely invisible to ordinary perception, is the one that concerns the particles you are made of. The protons and neutrons inside every nucleus of every atom in your body. The structures that have been there since the atoms in your body were assembled in the interiors of stars that died before the sun formed. They are stable enough to have lasted this long. Whether they are stable enough to last forever is a different question. And the answer to that question, which physicists have been trying to determine for decades using some of the most extraordinary experimental apparatus ever built, is more unsettling than most people know. If this is the kind of thinking that you find at the end of a long day, that patient dismantling of the obvious until something more interesting appears underneath, then Nocturnal Space is exactly where you are supposed to be. Subscribe now. Turn on notifications. Because what follows from here goes significantly deeper than the emptiness of atoms. It goes to the constants that make atoms possible, to the vacuum that atoms move through, to the forces that will eventually overcome everything that atoms have built. And it ends somewhere that changes what the solidity you feel right now actually means. The illusion of permanence is beautiful. What lies underneath it is more interesting still. In a mountain in Japan, 1,000 meters beneath the surface, inside a cylindrical tank holding 50,000 metric tons of the purest water ever produced by human technology, 11,129 light sensors are watching. Not watching for intruders, not monitoring for contamination, watching for something far stranger. They are watching for the moment when a proton, one of the fundamental building blocks of atomic matter, decides to stop existing. The experiment is called Super Kamiokande. It has been running since 1996. Every day the sensors stare into the ultra-pure water, waiting for a specific flash of light that would indicate that a proton inside one of the water molecules has spontaneously converted itself into other particles and vanished. The water is pure because impurities would introduce background radiation that could mimic the signal. The mountain is necessary because cosmic rays from space would trigger false positives in any surface detector. The sheer volume of water, 50,000 metric tons, is required because the event the physicists are looking for is so rare that you need an enormous number of protons watched simultaneously to have any reasonable chance of detecting it within a human lifetime. After nearly 3 decades of continuous operation, Super Kamiokande has not found what it is looking for. Not a single confirmed proton decay event. And this result, which might sound like good news, is one of the more unsettling outcomes in the history of experimental physics, for reasons that require understanding what proton decay would mean if it exists and what its absence might mean if it does not. Start with the proton itself. A proton is not a fundamental particle. It is a composite object made of 3 quarks, held together by the strong nuclear force, the most powerful of the 4 fundamental forces in nature, carried by particles called gluons that act as the glue between quarks. 2 up quarks and 1 down quark, bound together by an exchange of gluons so energetic and so continuous that the mass of the 3 quarks accounts for only about 1% of the proton's total mass. The other 99% is pure binding energy, the energy of the strong force holding the system together, made manifest as mass through Einstein's equivalence of energy and mass. This binding is extraordinarily robust by the standards of nuclear physics. The strong force is roughly 100 times more powerful than electromagnetism, which is itself vastly more powerful than gravity at nuclear scales. It takes enormous energy to pull a proton apart, which is why particle accelerators require billions of dollars of infrastructure to do it. In everyday environments, at the temperatures and energies present anywhere outside of stellar interiors or particle physics experiments, protons are essentially indestructible by any external force available to nature. But indestructible by external force is not the same as stable from within. The question of whether a proton can spontaneously decay, converting itself into lighter particles without any external energy input, is one of the most important open questions in particle physics. It is not a fringe question. It sits at the center of some of the most ambitious theoretical frameworks ever developed for understanding the deep structure of matter. Grand unified theories, which attempt to merge the strong force, the electromagnetic force, and the weak nuclear force into a single unified description, almost universally predict that proton decay should exist. The differences between the theories involve how fast it should happen, not whether it should happen at all. The predicted lifetime of the proton in the simplest grand unified theories was approximately 10 to the power of 30 to 10 to the power of 31 years. When early versions of Super Kamiokande and its predecessor Kamiokande began operating in the 1980s and 1990s, they quickly ruled out these simple predictions. No decay was found at those rates. The theoretical landscape shifted. More sophisticated models pushed the predicted lifetime to 10 to the power of 33 to 10 to the power of 35 years. Current experimental limits from Super Kamiokande place the proton lifetime at greater than approximately 10 to the 34th power years for the most commonly predicted decay modes. The simple models have been ruled out. The more sophisticated models are being constrained, but the more sophisticated models have not been eliminated. 10 to the power of 34 years. Hold this number against the age of the universe. The universe is approximately 1.38 times 10 to the 10th power years old. A proton lifetime of 10 to the 34th power years is longer than the age of the universe by a factor of roughly 1 trillion. The proton, if it decays, does so on timescales that make the current age of the universe look like the first nanosecond of a years-long process. This seems safe until you consider what proton decay would actually mean if it occurs, even at these extraordinary timescales. Every nucleus of every atom in the observable universe contains protons. Your body contains approximately 7 times 10 to the 27th power protons. The Earth contains approximately 10 to the 50th power protons. The observable universe contains an estimated 10 to the power of 80 protons. If protons decay on timescales of 10 to the power of 34 years, then over sufficient time, every nucleus that currently exists will dissolve. Not through collision or heating or any external process. Simply by waiting. The iron in your blood will not remain iron. The carbon in your DNA will not remain carbon. The oxygen in the air will not remain oxygen. Every element heavier than the decay products of proton disintegration, which are generically lighter particles and radiation, will eventually be converted to those lighter products and nothing else. In the very long run, proton decay means that the periodic table is temporary. The entire structure of chemistry, which is the structure of how atoms combine based on their electron configurations, which depends entirely on what atoms exist, which depends entirely on what nuclei are stable, rests on the assumption that protons persist. If they do not persist, then chemistry itself has an expiration date. Not soon. Not within any timescale relevant to life as we know it. But the expiration date is there, written into the structure of matter if grand unified theories are correct. The neutron adds its own chapter to this story, and in some ways a more immediately visceral one. A neutron inside a stable atomic nucleus is, for practical purposes, permanent. The nuclear environment stabilizes it, but a free neutron, a neutron that has been knocked loose from its nucleus and is traveling through space or through matter without being part of a nuclear structure, is not stable at all. A free neutron decays with a half-life of approximately 14 minutes and 38 seconds. In that time, it converts itself into a proton, an electron, and an antineutrino through a process called beta decay. Leave a neutron alone for 15 minutes, and there is a roughly 50% chance it no longer exists in its original form. This fact has implications that most people never encounter. The neutrons inside atomic nuclei are stable because the nuclear strong force and the specific energy balance of the nucleus keep them confined. Remove that confinement and the clock starts ticking immediately. Nuclear reactors produce free neutrons in enormous quantities as a byproduct of fission, and managing those neutrons, accounting for their decay, is a fundamental part of reactor physics. Neutron stars, which are objects the size of a city composed almost entirely of neutrons packed to nuclear density, are stable only because the gravitational pressure is sufficient to prevent the neutrons from undergoing beta decay. Reduce that pressure even slightly, and the neutrons begin converting to protons, releasing energy and changing the star's structure. The stability of matter, the reliability of the atomic nuclei that make chemistry possible, is not an intrinsic property of neutrons and protons. It is a property of the specific environments in which they find themselves. Take a neutron out of its nucleus and it has a quarter hour before it transforms into something else. The atom is stable because it is structured in a way that prevents its components from doing what they would do if left to their own devices. Super Kamiokandé's null result, its failure to detect proton decay, despite decades of operation, does not prove that protons are stable forever. It establishes a lower bound on the proton lifetime. It says that if proton decay exists, it must happen more slowly than the experiment can detect. Each year of operation extends this lower bound slightly, ruling out slightly slower decay rates. The experiment is currently being upgraded to an even larger detector called Hyper-Kamiokande, with approximately 10 times the water volume, which will extend the sensitivity further. The search will continue. The physics community has not concluded that proton decay is impossible. It has concluded that it is either very slow or very well hidden from current instruments. There is a deeper issue here that the proton decay question illuminates without fully resolving. The standard model of particle physics, the most successful scientific theory in the history of science in terms of predictive accuracy, does not predict proton decay at any rate. In the standard model, baryon number, roughly the number of protons and neutrons, is a conserved quantity. It cannot decrease through any process the standard model describes. If proton decay exists, it is evidence of physics beyond the standard model. If it does not exist, then the exact conservation of baryon number requires an explanation, because the same asymmetry between matter and antimatter that allowed the universe to consist of matter rather than annihilating back to pure radiation shortly after the Big Bang seems to require processes that violate baryon conservation. The universe itself appears to be evidence that baryon number is not exactly conserved, but we have never directly observed it being violated. This is the texture of the atomic fragility layer. Not a single clean answer, but a web of contingencies, each thread connected to others, none of them pulling free into certainty. The atoms are stable enough to have lasted 13.8 billion years since the Big Bang forged the first nuclei. They are stable enough to have allowed chemistry and biology and civilization to develop on at least one rocky planet in an outer spiral arm of an ordinary galaxy. But the physics that describes them most completely does not guarantee their permanent stability. It describes conditions under which they are stable and conditions under which they are not, and leaves open the question of whether the conditions we observe are truly permanent or merely long-lasting. And the atomic layer is the most familiar of the five. The one closest to ordinary experience, the one most directly connected to the matter you interact with every day. The next layer down is not about the particles themselves. It is about the rules that govern the particles, the specific numerical values that determine how strongly the forces act and how massive the particles are. Values that appear in the equations of physics without explanation, measured and accepted but not derived from any deeper principle. Values that, if they were even fractionally different, would produce a universe so unlike our own that the word universe would barely apply to both. Those values are not guaranteed either, and the story of why they have the values they do and what it would mean if they were otherwise is where the fragility of physical reality becomes genuinely difficult to dismiss as an abstract concern. There are approximately 20 numbers that run the universe, not approximately 20 laws, not approximately 20 principles, not approximately 20 theoretical frameworks. 20 numbers, specific numerical values that appear in the equations of physics as constants, measured by experiment and accepted as given, not derived from any deeper theory, not explained by any more fundamental principle. The speed of light, the gravitational constant, the mass of the electron, the charge of the electron, the strength of the strong nuclear force, the strength of the electromagnetic force, the cosmological constant, Planck's constant, the ratio of the proton mass to the electron mass, and roughly a dozen others. These numbers are the operating parameters of physical reality. They determine how strongly gravity pulls, how fast light moves, how tightly quarks bind inside protons, how electrons distribute themselves around nuclei to create the chemical properties of atoms. Every structure in the observable universe, from the hydrogen atom to the human brain to the Andromeda galaxy, exists because these numbers have the values they have. Chemistry works because these numbers have the values they have. You exist because these numbers have the values they have. Here is what makes this deeply unsettling. No one knows why they have these values, not approximately, not in a way that requires refinement, not at all. The most complete and successful physical theories ever constructed, theories that predict experimental outcomes to 12 decimal places of accuracy, simply insert these numbers from measurement without explaining where they come from or why they could not have been otherwise. They are, in the technical language of physics, free parameters. Free parameters means they are free to take any value. The equations work regardless of what value you plug in. The universe, however, does not work regardless of what value you plug in. It works only for a narrow range of values centered very close to the ones we observe. How narrow is narrow? This is where the numbers become either the most remarkable coincidence in the history of science or evidence of something about the universe that current physics cannot account for. Consider the strong nuclear force, the force that binds quarks together inside protons and neutrons, and binds protons and neutrons together inside atomic nuclei. Its strength is characterized by a coupling constant that physicists denote as alpha S. The actual value of this constant at the energy scales relevant to nuclear physics is approximately 0.118. Now ask what happens if this number is different. If the strong force were approximately 2% stronger than it is, the physics of the very early universe would change in a specific and catastrophic way. In the first minutes after the Big Bang, nuclear fusion produced the lightest elements: hydrogen, helium, tiny amounts of lithium. This process, called Big Bang nucleosynthesis, produced a universe that is approximately 75% hydrogen and 25% helium by mass. That ratio is the raw material for everything that followed. Stars burn hydrogen. Hydrogen combines with oxygen to make water. Carbon, nitrogen, oxygen, and the other elements of biology are produced in stellar interiors from hydrogen and helium. With a strong force 2% stronger, the deproton, a nucleus consisting of 2 protons with no neutrons, would be stable. In our universe, the deproton is unstable and decays almost immediately. This instability is not a flaw. It is the mechanism that makes stars burn slowly enough to last billions of years rather than exploding in an instant. If the diproton were stable, hydrogen would fuse into it in the early universe with extraordinary efficiency. Almost no hydrogen would survive Big Bang nucleosynthesis. The universe would be overwhelmingly helium from its earliest moments. No hydrogen means no water. No water means no liquid solvent for the chemistry of life. No long-burning stars means no stable energy source for billions of years of biological evolution. A universe 2% stronger in its nuclear force is a universe without chemistry, without water, without anything resembling the conditions that produced you. If the strong force were approximately 5% weaker, the deuteron, the nucleus of deuterium, consisting of 1 proton and 1 neutron, would be unbound. Deuterium is the first step in the proton-proton chain, the nuclear reaction that powers stars like the Sun. Without stable deuterium, the proton-proton chain cannot proceed. Stars cannot fuse hydrogen. The universe fills with hydrogen that has no mechanism for converting itself into heavier elements. No stellar nucleosynthesis means no carbon, no oxygen, no nitrogen, no iron, no calcium. No elements beyond hydrogen means no periodic table. No periodic table means no chemistry. A universe 5% weaker in its nuclear force is a universe of pure hydrogen, forever. 2% stronger or 5% weaker. That is the range within which a change to a single constant produces a universe incompatible with chemistry. The actual value sits within this window. The window is not large relative to the range of values the constant could in principle take, which spans many orders of magnitude. The electromagnetic force presents a similar picture. The electromagnetic coupling constant, alpha, has a value of approximately 1/137, a number so specific and apparently arbitrary that Richard Feynman, one of the founders of quantum electrodynamics, called it one of the greatest mysteries of physics and suggested that every physicist should have it tattooed on the back of their hand as a reminder of how much is not understood. The specific value of alpha determines the size of atoms, the energies of chemical bonds, the spectrum of light emitted and absorbed by different elements, and the precise way electrons distribute themselves around nuclei to create the chemical properties of every element in the periodic table. If alpha were significantly larger, atoms would be smaller and chemical bonds would be stronger. But the increased electromagnetic repulsion between protons in large nuclei would prevent heavy elements from existing. If it were significantly smaller, atoms would be larger, chemical bonds would be weaker, and the chemistry of complex molecules would be disrupted. The specific value of 1/137 is required, within a range that is not wide, for chemistry to work in the way that makes biology possible. The cosmological constant, the parameter that characterizes the energy density of empty space and drives the accelerating expansion of the universe, is the most extreme example of fine-tuning in all of physics. Quantum field theory, the theoretical framework that underlies the Standard Model and is the most precise physical theory ever developed, predicts a value for the cosmological constant based on the energy of quantum fluctuations in the vacuum. The predicted value is approximately 10 to the power of 120 times larger than the observed value. Not 10 times larger, not 1,000,000 times larger. 10 to the power of 120 times larger. This discrepancy of 120 orders of magnitude is the largest disagreement between theory and observation in the history of science. Physicists call it the cosmological constant problem and describe it without irony as the worst prediction in the history of physics. The theoretical value would produce a universe expanding so rapidly that no structure could ever form. Galaxies would never condense. Stars would never ignite. Planets would never coalesce. The universe would be a rapidly expanding fog of particles, thinning toward emptiness before any chemistry could occur. The fact that the observed value is so much smaller than the theoretical prediction is not explained by any current theory. The cancellation between the theoretical contributions that would produce the large predicted value and whatever produces the small observed value must be extraordinarily precise, to 120 decimal places, and no mechanism for this cancellation is known. The ratio of the proton mass to the electron mass is approximately 1,836. This specific ratio determines the structure of atoms in ways that make chemistry work. If it were much smaller, electrons would be more energetic relative to protons and chemical bonds would be disrupted. If it were much larger, electrons would effectively be pinned to nuclei, and the flexible electron behavior that makes chemical bonding possible would be eliminated. The value 1,836 is not derived from any theory. It is measured and inserted into the equations. Why it is 1,836 rather than 100 or 10,000 is unknown. The pattern across all of these constants is the same. Each one sits within a range of values that permits chemistry, biology, and complexity. The range is not generous. Moving any of them by amounts that seem small on a logarithmic scale produces universes where no atoms exist, or where only hydrogen exists, or where stars burn out in seconds, or where the expansion of space prevents any structure from forming. The universe is fine-tuned in the sense that the actual values of its fundamental constants lie within the narrow windows that permit complexity. But this is not a controversial claim. It is an observation about the mathematics that even physicists who resist its implications acknowledge as real. What is controversial is what this fine-tuning means. One response is the anthropic principle. In a universe not fine-tuned for complexity, no one exists to observe that it is not fine-tuned. The fact that we observe a universe fine-tuned for our existence is therefore not surprising, because non-fine-tuned universes contain no observers. This logic is valid as far as it goes, but it requires something to select among possible universes. If there is only one universe, with one set of constants, then the anthropic principle provides no explanation at all. It simply relabels the mystery. The multiverse hypothesis provides the something. If there are a vast number of universes, yes, each with different values of the fundamental constants, then some of them will by chance have constants in the windows that permit complexity. Observers will find themselves in those universes for the same reason that you find yourself on a planet with liquid water rather than on one of the far more numerous rocky objects without it. The selection effect is real. The fine-tuning is explained not by design, but by the combination of variation across possible universes and the selection filter of observer existence. The multiverse is not currently testable in any direct way. Some cosmological models that predict inflation, the rapid early expansion of the universe, also predict a multiverse as a consequence, and inflationary cosmology has observational support from the cosmic microwave background. But the multiverse itself remains beyond direct observation by construction, since other universes with different constants are causally disconnected from ours. The fine-tuning argument for the multiverse is logical but not empirically confirmed. The third response is that the fine-tuning is pointing at something genuinely unknown about the structure of physics, that the apparent freedom of the constants is an illusion produced by the incompleteness of current theory, that a deeper theory, not yet formulated, will show that the constants are not free parameters at all, but have the values they do for reasons that will eventually be understood. This hope has motivated decades of work on string theory, loop quantum gravity, and other approaches to quantum gravity. None of them has yet produced a derivation of the observed constant values from more fundamental principles. The hope persists, but has not been rewarded. What is not available is the option of dismissing the fine-tuning as unimportant. The constants could have been otherwise. The mathematics does not prevent them from being otherwise. A universe with different constants would not be slightly different from ours. It would be, in almost all cases, utterly devoid of any structure more complex than a uniform distribution of elementary particles. The constants we observe are the specific values that thread the needle between sterility in one direction and sterility in the other. That threading is real, its explanation is unknown, and the constants are not the deepest layer of fragility. They describe the rules that govern particles and forces within spacetime. But spacetime itself, the fabric in which the particles move and the forces act, may be fragile in a way that makes the fine-tuning of constants feel, by comparison, like a manageable engineering problem. The vacuum you are moving through right now, the space between atoms in your body and between planets in the solar system, and between stars in the galaxy. That vacuum may not be what it appears to be. It may not be empty in any fundamental sense, and the state it is currently in may not be the most stable state it can occupy. And if it is not, then everything built on top of it, every atom, every star, every galaxy, every mind that has ever existed, is built on a foundation that could shift without warning and without any mechanism for recovery. On the 4th of July, 2012, in a seminar room at CERN, the European Organization for Nuclear Research, a physicist named Fabiola Gianotti presented data from the Large Hadron Collider that brought the audience to its feet. The Higgs boson had been found. The particle predicted by Peter Higgs and others in 1964 as the quantum excitation of the field responsible for giving mass to other particles had finally been directly observed, nearly 50 years after its prediction, using the most complex scientific instrument ever built by human beings. The discovery completed the standard model of particle physics. It confirmed that the theoretical framework physicists had spent decades developing was correct in its most essential remaining prediction. It was, by any measure, one of the greatest triumphs in the history of science. Within weeks of the announcement, a group of physicists sat down to calculate what the discovery actually meant. Specifically, they wanted to know what the measured mass of the Higgs boson, 125.1 billion electron volts, implied about the stability of the vacuum state of the universe. The vacuum state is the lowest energy configuration of the quantum fields that permeate all of space. It is what space is when nothing is in it. It is the ground on which all of physics is built. The calculation they performed was not speculative. It was straightforward application of known physics, combining the measured Higgs mass with the measured mass of the top quark, the heaviest known fundamental particle, to determine where the universe sits on the energy landscape of possible vacuum states. The result of this calculation, which has been refined and confirmed by multiple groups in the years since, is that the universe appears to be in a metastable vacuum state, not the lowest energy state possible, a state that is locally stable, meaning small perturbations return to the same configuration, but not globally stable, meaning there exists a lower energy configuration that the universe could in principle transition to. To understand what this means, consider a familiar analogy that the physics community has used repeatedly because it captures the essential structure of the situation. Imagine a marble resting in a small bowl, which is itself sitting on a table. The marble is stable in its bowl. Small nudges will displace it slightly, but it will roll back to the bottom of the bowl and settle. This is local stability. But the bowl is sitting on a table, and the floor is far below. If the marble somehow escaped the bowl and reached the table surface, it would roll off the table and fall to the floor. The floor is a lower energy state. The marble in the bowl is metastable. It is not in the lowest energy configuration available to it. It is in a local minimum, not the global minimum. It is stable against small disturbances, but vulnerable to large ones or to quantum tunneling through the barrier, separating it from the lower energy state. The vacuum of the universe, the fabric of space itself, appears to be in exactly this situation. The Higgs field, which permeates all of space and gives mass to particles through its interaction with them, has a specific value throughout the universe. That value corresponds to the current vacuum state, but the equations governing the Higgs field, when evaluated with the measured parameters of the standard model, reveal that there exists another possible vacuum state at a lower energy density, separated from the current state by an energy barrier. The universe is in the bowl. The floor exists. The barrier between them is extremely high, which is why the current state has lasted 13.8 billion years. But high is not infinite. Quantum mechanics permits a process called vacuum decay, or vacuum tunneling, in which the Higgs field can spontaneously transition from the current metastable state to the true vacuum state through quantum tunneling. This does not require the universe to go over the energy barrier. It requires only that the quantum uncertainty of the field allows it to tunnel through the barrier to the other side. The way a particle in quantum mechanics can appear on the far side of a barrier, it classically should not be able to cross. The probability of this happening at any given point in space at any given moment is extraordinarily small, so small that the expected lifetime of the current vacuum state, based on current calculations, is estimated to be somewhere around 10 to the power of 400 years or longer, a number that dwarfs even the timescales discussed in the previous segment, and that is far longer than any plausible physical process that might end the universe by other means. But small probability is not zero probability, and the transition, if it occurs, would not be a local event. When vacuum decay occurs at a point in space, the result is the formation of a bubble of true vacuum at that location. Inside the bubble, the Higgs field has its true vacuum value, which is different from the current value. The particle masses inside the bubble are different. The strength of the electromagnetic force inside the bubble is different. The chemistry inside the bubble is different. Everything inside the bubble obeys different laws of physics from the laws operating outside it, and the bubble does not stay small. There is no restoring force that would pull the bubble wall back. The true vacuum state has lower energy than the metastable state, which means it is energetically favored. The bubble wall expands outward at the speed of light, converting metastable vacuum to true vacuum as it goes, driven by the energy difference between the two states, at the speed of light in every direction simultaneously. This is the feature of vacuum decay that distinguishes it from every other catastrophe in this video or in any other discussion of cosmic threats. An asteroid impact is detectable years or decades in advance. A supernova in our galaxy would be visible before its radiation arrived. The expansion of the sun into a red giant will be preceded by billions of years of gradual change. Even the heat death of the universe proceeds on timescales that allow, in principle, arbitrarily long periods of awareness before the final dissolution. Vacuum decay provides no warning. The bubble wall travels at the speed of light. No information can travel faster than light. No signal from the bubble wall can precede it. No observation of the approaching transition is possible because the light carrying that information travels at the same speed as the wall itself. One moment you exist, the next moment you do not. Not destroyed in the sense of your atoms being scattered or your temperature being raised to lethal levels. Replaced. The atoms that constitute you would not survive the transition intact because the laws of physics governing atomic structure would change the instant the bubble wall passed through your location. The electromagnetic force that holds electrons in orbit around nuclei would have a different strength in the true vacuum. The quarks inside protons would respond to a different strong force constant. The Higgs field would have a different value, which means every particle that acquires its mass from the Higgs field would have a different mass. The specific masses and force strengths that allow stable atoms to exist are features of the current vacuum state. The true vacuum has different features. There is no reason to expect that the specific combination of particle masses and force strengths in the true vacuum would permit stable atoms, much less complex chemistry, much less anything resembling the conditions that produced life in the current vacuum. The transition would not be painful. It would not be frightening. There would be no experience of it whatsoever, because experience requires the continuation of the physical processes that produce consciousness, and those processes require the specific laws of physics operative in the current vacuum, which would be instantly replaced. The ending would not be experienced as an ending. It would simply be the last thing, followed by nothing capable of registering that it was the last thing. The absence of any warning, any gradual approach, any detectable precursor is philosophically distinct from other threats in a way worth dwelling on. Human psychology is calibrated to threats that approach, that escalate, that provide opportunity for response. The evolution that shaped human cognition operated in an environment where dangers were visible before they arrived, where preparation and avoidance were possible, where the distance between perceiving a threat and responding to it mattered. Vacuum decay is categorically outside this framework. It is not a threat you can see coming. It is not a threat you can prepare for. It is not a threat you can mitigate. If it happens, the only facts relevant to your experience are that you were here and then you were not, and neither state contains any awareness of the transition between them. There is, however, a significant complication to the picture that the stability calculations suggest. The calculation that places the universe in the metastable regime depends critically on the value of the top quark mass, which is measured at particle accelerators and carries experimental uncertainty. Small changes in the top quark mass shift the calculated stability of the vacuum. Within the current experimental uncertainties, the universe is consistent with being in three different regimes. It could be in the unstable regime, where the current vacuum is not even locally stable and decay is inevitable on some timescale. It could be in the metastable regime, where the current vacuum is locally stable but not globally stable, and decay is possible but extremely unlikely on any human-relevant timescale. Or it could be in the stable regime, where the current vacuum is the true ground state and no decay is possible. The most probable regime given current measurements is metastable, with the universe sitting close to the boundary between metastable and stable. This boundary is called the critical line, and the apparent proximity of the universe's parameters to this line is itself a puzzle. There is no known reason why the Higgs mass and top quark mass should be tuned to values near the critical boundary between stability and metastability. Some physicists regard this near criticality as significant, possibly pointing toward new physics beyond the standard model that would explain it. Others regard it as a coincidence within the uncertainties. The question cannot be resolved without either more precise measurements of the relevant parameters or a theoretical framework that predicts their values from more fundamental principles. What can be said with confidence is this: the quantum field that fills all of space and gives mass to all particles is not guaranteed to remain in its current configuration. The laws of physics that make atoms, chemistry, and life possible are features of a specific vacuum state that may not be the lowest energy state available. The universe has been in this configuration for 13.8 billion years without incident, which is consistent with an extremely long but not infinite stability lifetime. And if the transition occurs, it occurs at the speed of light with no warning and with consequences for the structure of matter that make the concept of survival inapplicable. The expected waiting time before such an event is so long that it exceeds the timescales of every other threat to the universe's structure by margins that render comparison meaningless. The universe will almost certainly end by heat death, or by the evaporation of the last black hole, or by proton decay, long before vacuum decay would be expected to occur based on current calculations. In practical terms, vacuum decay is not a threat. It is a feature of physical reality that illuminates something important about the nature of the ground we stand on. That something is this: the laws of physics you rely on every moment of every day. The specific rules that allow atoms to be stable and chemistry to work and your neurons to fire in the patterns that constitute thought are not eternal. They are features of a particular configuration of a quantum field. That configuration has lasted long enough for 13.8 billion years of cosmic evolution to occur, for stars to form and die and scatter heavy elements, for planets to coalesce and cool, for chemistry to produce biology, and biology to produce minds capable of calculating the stability of the vacuum they inhabit. All of that is real. None of it is guaranteed to continue indefinitely by any principle more fundamental than the stability of the current vacuum state, which is itself not guaranteed by anything more fundamental than the specific values of the Higgs and top quark masses that were set in the first moments after the Big Bang. The ground beneath everything is not bedrock. It is a field in a particular configuration, held there by an energy barrier of finite height, persisting because quantum tunneling through that barrier is extraordinarily improbable, not because it is impossible. The distinction between extraordinarily improbable and impossible is the distinction between a universe that has lasted 13.8 billion years and a universe that is guaranteed to last forever. The first is what we have. The second is what intuition suggests. The difference between them is the fragility at the center of this story. What remains is the cosmic scale. The forces operating not at the quantum level of fields and particles, but at the scale of galaxies and the universe itself. The expansion that is carrying everything apart. The entropy that is grinding every structure toward dissolution. And the timeline of that dissolution, which extends so far into the future that the Higgs field stability calculation, with its 10 to the power of 400-year estimate, sits near the beginning of the story rather than its end. That story is where the fragility becomes not just real but total, and it is where the video makes its turn toward the question of what all of this actually means. In 1998, two teams of astronomers were racing to answer what seemed like a straightforward question. The universe has been expanding since the Big Bang. Gravity pulls matter together. Therefore, the expansion should be slowing down. The question was how fast it was slowing, and whether it would slow enough to eventually reverse, pulling everything back together in a big crunch, or whether it would continue expanding forever, growing colder and more diffuse as the stars burned out one by one. Both teams were using the same tool to answer it. Type 1, A supernovae, the thermonuclear explosions of white dwarf stars that always detonate at approximately the same intrinsic brightness, making them reliable distance markers across billions of light years. Measure how bright they appear, compare to how bright they should be at their measured distance, and you can determine whether the expansion is faster or slower than models predict. Both teams found the same answer. The supernovae were dimmer than expected, not slightly dimmer, measurably, consistently, reproducibly dimmer across independent observations spanning different telescopes, different observing programs, and different methodologies. Dimmer meant farther. Farther meant the universe had expanded more than predicted. More expansion than predicted meant not deceleration but acceleration. The universe was not slowing down, it was speeding up. Something was pushing space apart faster and faster with each passing year, overcoming the gravity that should have been winning and replacing deceleration with an acceleration whose cause was entirely unknown. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery. The something was named dark energy, a placeholder acknowledging that its nature was unknown and that the two words were chosen to signal mystery rather than understanding. Dark because it emits no light and cannot be detected directly. Energy because it has the effect of an energy density distributed uniformly through space, driving expansion rather than resisting it. What dark energy actually is remains one of the deepest unsolved problems in physics. The leading candidate, the cosmological constant, interprets it as an intrinsic energy of empty space itself, a fixed energy density that does not dilute as space expands. But as established in the previous segment, the predicted value of this energy density from quantum field theory disagrees with the observed value by 120 orders of magnitude, which means the cosmological constant explanation works descriptively while failing completely at the level of mechanism. What is established beyond reasonable doubt is what dark energy does. It constitutes approximately 68% of the total energy content of the observable universe. Ordinary matter, the atoms and molecules and stars and planets and everything visible, constitutes approximately 5%. Dark matter, the gravitationally influential but electromagnetically invisible substance that shapes galaxy formation and cluster dynamics, constitutes the remaining 27%. The universe is overwhelmingly composed of things we do not understand. The visible, tangible, chemistry-bearing portion of reality is a 5% minority in a cosmos dominated by substances that defeat every attempt at direct detection, and the dominant component, dark energy, is working against every structure that gravity has spent 13.8 billion years assembling. Gravity is attractive. It pulls matter together. It assembled the hydrogen clouds of the early universe into the first stars. It collapsed those stars and their descendants into the galaxy-seeding black holes that anchored the formation of the Milky Way and Andromeda and every other galaxy in the observable universe. It holds the Earth in its orbit, and the Moon in its orbit, and the atmosphere against the surface. Gravity built everything you see when you look at the night sky and everything you walk on when you step outside. It is the architect of cosmic structure. Dark energy is repulsive at cosmic scales. It does not pull matter together. It pushes space apart. And because it does not dilute as space expands, its influence grows relative to gravity as the universe grows. In the early universe, matter was dense and gravity dominated. The cosmic web of filaments and voids assembled under gravity's influence. Galaxies formed, clusters formed, structure developed at every scale. But as the universe expanded and matter became more dilute, the ratio of dark energy to matter shifted. Approximately 5 billion years ago, the ratio crossed the threshold at which dark energy's repulsive effect exceeded gravity's attractive effect at cosmic scales. The expansion of the universe transitioned from deceleration to acceleration. The universe shifted from a regime where gravity was building structure to a regime where dark energy is dismantling the possibility of further structure formation on the largest scales. The galaxies currently visible from Earth are not all permanently visible. Galaxies beyond a certain distance are receding from us faster than light can cross the expanding space between us and them. This is not a violation of relativity, which prohibits objects from moving through space faster than light, not space itself from expanding faster than light. The result is a cosmic horizon beyond which newly emitted light can never reach us. Galaxies beyond this horizon are already lost in the practical sense that no future signal from them will ever arrive. And because the expansion is accelerating, the horizon is not fixed. The volume of observable universe is shrinking as dark energy carries more and more galaxies beyond the point of no return. In approximately 150 billion years, every galaxy beyond our local gravitational group will have been carried past the cosmic horizon. The night sky will be dark except for the stars of the merged Milky Way and Andromeda galaxy, which will by then have completed their collision and settled into a single large elliptical galaxy. The evidence for cosmic expansion, for the existence of other galaxies, for the scale of the universe, will have been erased from any observer's accessible sky. Future astronomers will look outward and see nothing. They will have no way of knowing that the universe contains 2 trillion galaxies rather than one. But the local group is not immune. Gravity holds the local group together against the expansion, but the local group is not infinite. On timescales of tens of billions of years, the individual galaxies within the local group will merge into a single object. The merged remnant will be gravitationally stable against the expansion of space because it is bound tightly enough that dark energy cannot overcome the internal gravity. But the merged galaxy itself will not escape the thermodynamic processes that are dismantling every structure in the universe at a slower but equally inevitable pace. Entropy is the second force tearing everything apart, and unlike dark energy, entropy requires no new physics and no unknown substance. It is the most firmly established principle in all of science, confirmed by every experiment ever conducted, required by the statistical mechanics of any system containing large numbers of particles. The second law of thermodynamics states that the entropy of an isolated system never decreases. In every physical process, the total disorder either increases or remains the same. Heat flows from hot to cold, and never spontaneously from cold to hot. Concentrated energy disperses. Organized structures develop from energy flows and eventually dissolve when those flows cease. The universe, as an isolated system, is subject to the second law without exception. Stars exist as local violations of this tendency, temporary concentrations of hot matter that radiate energy into the cold void and thereby increase the entropy of the universe as a whole, even as they maintain low entropy locally. Every photon a star emits is one more step toward the equilibrium that the second law demands. Stars are entropy-generating machines. Their light and heat, which sustains everything from the photosynthesis of plants to the warmth of planetary surfaces, is entropy production in process. The universe pays for every moment of stellar luminosity with an increase in total disorder that cannot be undone. Stars have finite fuel. Hydrogen is consumed in stellar cores and converted to helium, and then to heavier elements through successive fusion stages. When the fuel runs out, the star ends. Small stars like the Sun will exhaust their hydrogen over timescales of 10 billion years and end as white dwarfs, slowly cooling embers that radiate their residual heat over trillions of years. Massive stars burn faster and end in supernova explosions, leaving neutron stars or black holes. Red dwarfs, the most numerous stellar type, burn so slowly that they will last for trillions of years, but they will also eventually exhaust their fuel. The star formation rate of the universe peaked approximately 10 billion years ago and has been declining since. The universe is past its stellar prime. On timescales of approximately 100 trillion years, the last stars will exhaust their fuel. The era of stellar light will end. What remains will be a universe populated by cooling white dwarfs, neutron stars, and black holes, all in the dark, all slowly radiating their residual energy into a universe growing colder with every passing moment. White dwarfs will cool over quadrillions of years, eventually reaching thermal equilibrium with the ambient temperature of the universe, which will itself have dropped far below the current 2.7 Kelvin of the cosmic microwave background as expansion stretches even those ancient photons to longer wavelengths and lower energies. Black holes will be the last significant structure standing, but black holes are not permanent either. Stephen Hawking demonstrated in 1974 that black holes emit thermal radiation through a quantum mechanical process at their event horizons, a phenomenon now called Hawking radiation. This emission carries energy away from the black hole, reducing its mass slowly but continuously. Given enough time, any black hole will evaporate completely, converting its mass entirely into Hawking radiation and dispersing into the void. The timescale for this process depends on the black hole's mass. A stellar mass black hole requires approximately 10 to the power of 67 years to evaporate. The supermassive black hole at the center of the Milky Way, approximately 4 million solar masses, requires roughly 10 to the power of 87 years. The most massive black holes known, billions of solar masses, require approximately 10 to the power of 100 years. After the last black hole evaporates, the universe will contain nothing but diffuse photons, neutrinos, electrons, and positrons, all at extremely low energy, all expanding apart, none of them interacting at any significant rate, the universe approaching but never quite reaching the absolute thermal equilibrium that the second law demands as its endpoint. The temperature will be so low, the density so negligible, the interactions so rare, that no structure of any kind can form or persist. This state, called heat death, is not an explosion or a collapse or any dramatic event. It is the final victory of entropy. The universe will not end. It will simply become incapable of anything interesting ever happening again. Against this backdrop, the Planck scale fragility adds one final unsettling layer. Everything described in this video, from atomic structure to vacuum stability to dark energy to entropy, is physics as it operates at scales much larger than the Planck length of 10 to the power of minus 35 meters and the Planck time of 10 to the power of minus 43 seconds. At those scales, the descriptions break down. General relativity, which describes gravity, and quantum mechanics, which describes everything else, are mutually inconsistent at Planck scales. The two most successful theories in the history of physics cannot both be correct at the smallest scales of space and time. Something is missing. The theory of quantum gravity that would reconcile them does not exist in a complete and tested form. What this means is that the bedrock of physical reality at the smallest scales is unknown. The behavior of spacetime at the Planck scale, where quantum fluctuations are large enough to significantly distort the geometry of space, where the smooth fabric of spacetime dissolves into something that current physics cannot describe, is genuinely beyond the reach of any confirmed theory. String theory, loop quantum gravity, and other approaches attempt to fill this gap, but none has been experimentally confirmed. The rules at the bottom of the structure may be very different from the rules we observe at larger scales, and those Planck scale rules, whatever they are, ultimately underlie everything built on top of them, including the vacuum stability calculations, the fine-tuned constants, and the thermodynamic processes driving heat death. What remains when all 5 layers of fragility have been laid out is not a picture of a universe about to collapse. The timescales are so long that the word soon becomes meaningless as a description of any of these processes. What remains is a picture of a universe that is, at every level of description, contingent rather than necessary, temporary rather than permanent, balanced rather than fixed. The protons may eventually decay. The constants could, in principle, have been otherwise. The vacuum may not be the deepest available. The dark energy will eventually overcome everything gravity built. The entropy will win in the end. These are not comfortable conclusions, but they are the conclusions that the physics actually supports. They are also, as the final segment of this video will show, the conclusions that make everything interesting about the universe possible in the first place. Everything established in this video is true. The protons may eventually decay. The constants of physics are fine-tuned to values that sit within narrow windows of compatibility with complexity, without any known explanation for why they have those values rather than others. The vacuum of space may be metastable, held in its current configuration by a barrier of finite height that quantum tunneling could in principle breach. Dark energy is winning its long contest with gravity, carrying galaxies beyond the cosmic horizon one by one, and eventually dismantling the possibility of any new structure forming at the largest scales. Entropy is grinding every organized system toward dissolution, and the second law guarantees that this grinding will not stop until the universe reaches a state of maximum disorder from which no further complexity can emerge. All of this is real. None of it is exaggerated. The physics is as solid as physics gets, and none of it is the problem it appears to be. Because the framing that presents fragility as the enemy of existence has the relationship exactly backwards. Consider what a non-fragile universe would look like. A universe in perfect thermodynamic equilibrium from its first moment would be a universe in which no temperature gradients existed, no energy flows from hot regions to cold, no possibility of the energy flow that every physical process from nuclear fusion to metabolism requires. A universe in which the vacuum was in its absolute ground state from the beginning would be a universe in which the Higgs field had a different value. Particle masses would be different, and there is no reason to believe the different masses and force strengths would permit stable atoms, let alone chemistry, let alone the 100-step sequence of coincidences that produced biology. A universe in which the fundamental constants were not fine-tuned, but simply fixed at values derivable from first principles would need to explain how those first principles managed to produce constants in the specific windows that permit complexity, and no such first principles exist in any confirmed theory. The universe that is maximally stable, maximally permanent, maximally non-fragile, is a universe in which nothing interesting happens. Stability and complexity are not compatible at the deepest level. They are, in a precise physical sense, alternatives. The stable universe is empty and cold and uniform and silent. The universe that permits stars and planets and oceans and organisms is the universe that is running down, that is not in equilibrium, that is maintaining structures far from their ground states by consuming energy flows that will eventually be exhausted. The fragility is not a failure mode of the universe. It is the operating mode, the specific mode in which complexity is possible. This is not a rhetorical move designed to make disturbing facts feel acceptable. It is a physical observation about the relationship between thermodynamic non-equilibrium and the possibility of organized structures. A life exists because the Earth is not in thermodynamic equilibrium with its surroundings. It is bathed in low-entropy sunlight, which it absorbs and re-emits as higher entropy infrared radiation, and the flow of entropy through this system is what powers every biological process from the photosynthesis of the first cell to the neural activity generating the thought you are having right now. Remove the entropy flow by putting the Earth in perfect thermal equilibrium with its environment, and every biological process stops immediately. Life is not something that happens despite thermodynamic non-equilibrium. It is something that happens because of it. Stars exist because the early universe was not in its ground state. The density fluctuations seeded by quantum mechanics during inflation, amplified by gravitational instability over hundreds of millions of years, produced the overdense regions that collapsed into the first stars. A universe that began in perfect uniformity would have no mechanism for structure formation. No stars means no heavy elements. No heavy elements means no rocky planets. No rocky planets means no geology, no oceans, no chemistry beyond hydrogen and helium. The specific imperfection of the early universe, its microscopic departure from perfect uniformity, is the seed from which everything we can see grew. The fine-tuning of constants, which is one of the most troubling aspects of the universe's fragility from a philosophical standpoint, can be reframed in the same way. The constants are not fine-tuned for life in some teleological sense that implies life was the goal. They are in a configuration that happens to permit complexity. What is remarkable is not that the constants permit complexity, but that a universe in which the constants permit complexity is a universe that exists at what appears to be a knife edge between two forms of sterility. Too strong a strong force, and there is no hydrogen. Too weak, and there are no heavy elements. Too large a cosmological constant, and there are no galaxies. Too small, and there is nothing to explain. The knife edge is where complexity lives. The knife edge is what fragility looks like from the outside. Vacuum metastability, the possibility that the universe is in a higher energy configuration than its true ground state, is perhaps the most viscerally unsettling of the 5 fragility layers because it suggests that the laws of physics we rely on are features of a temporary configuration rather than eternal features of reality. But consider the alternative. If the universe had always been in its true vacuum state, the Higgs field would have a different value. The mass of every fundamental particle would be different. The strength of every force would be different. Whether that different universe would permit stable atoms or chemistry or anything is unknown and unknowable from within our vacuum. What is knowable is that our vacuum, the metastable one, the temporarily configured one, is the one that permitted 13.8 billion years of increasing complexity, culminating in organisms capable of calculating the stability of the vacuum they inhabit. Whatever the true vacuum would have produced, it did not produce that in the regions of space we can observe. The relationship between fragility and complexity runs through every layer of the physical picture. Atoms are stable enough to allow chemistry, but the components they are made of are not permanently stable. This specific level of stability, high enough for chemistry to develop over billions of years but not infinite, is exactly what allows the universe to have a thermal history. A universe in which protons never decayed and all matter was eternal would be a universe in which the heat-death scenario plays out differently, where matter persists forever as cold, dark lumps rather than eventually dissolving, but where those lumps are equally incapable of interesting behavior. The fragility of nuclear matter on very long timescales is the final stage of a process that began with the fragility of the early universe and will end with the dissolution of everything that fragility built. There is a specific way that this reframing changes the emotional valence of everything established in this video. If you hear that the protons in your body may eventually decay, the natural response is to feel that something is being taken from you, that the universe is revealing a hidden flaw, a planned obsolescence built into matter at the deepest level. But the same fine-tuning that placed the proton lifetime at values long enough for chemistry to develop over billions of years also placed it short enough that the matter in the universe is not eternal. The proton lifetime is one of the constants that threads the needle between universes where matter never forms and universes where matter forms and lasts forever, but does nothing. Our universe is in the window where matter forms, develops complexity, and eventually dissolves. That window is narrow. Sitting in it is what fragility looks like from inside. The heat death of the universe, the final victory of entropy, is the most total of the fragilities, because it operates on everything without exception and leads to a state from which no recovery is possible. But heat death is only possible in a universe that was not in thermodynamic equilibrium at its beginning. The Big Bang produced an extraordinarily low entropy initial state. a universe of nearly uniform temperature and density with tiny quantum fluctuations that seeded all subsequent structure. That low initial entropy is the reservoir from which all the structure in the observable universe has been drawn. Every star, every galaxy, every living cell has been built by drawing on the entropy budget of the early universe, consuming low entropy and producing high entropy as the price of complexity. Heat death is not the universe failing. It is the universe completing the process that began with the Big Bang. The fragility was there from the first moment, written into the low entropy initial conditions that made everything else possible. You are reading these words at a specific moment in the universe's history, not the first moment, not the last. Somewhere in the middle of the stellar era, the 100-trillion-year window during which stars burn and planets exist, and the conditions for life are met in at least some locations. Before this era, the universe was too hot for atoms. After it, the universe will be too cold and too dark for anything energetic enough to produce consciousness. The stellar era is the window. You exist within it. Every living thing that has ever existed has existed within it. The entire history of life on Earth, from the first self-replicating molecule to whatever reads these words, has played out within this narrow slice of cosmic time. The window is fragile. It opened because of the specific initial conditions of the Big Bang, the specific values of the constants, the specific configuration of the vacuum, the specific balance between gravity and dark energy that has permitted structure to form and persist for long enough for biology to develop. Any of these could have been otherwise. None of them was otherwise, at least in the observable portion of the universe. And the result of their being as they are, rather than otherwise, is the existence of minds capable of tracing the physical history of the universe from the fluctuations of the cosmic microwave background, to the stability calculations of the Higgs field, to the entropy accounting of stellar evolution, to the question of what all of it means. That question, what does it mean that the universe is fragile in the ways this video has described, does not have a physical answer. Physics describes the fragility. It does not evaluate it. But the evaluation is available from within the fragility itself, from the minds that the fragile universe produced. And it is this: the fragility is not a problem. The fragility is the mechanism. Every layer of instability, from the quantum fluctuations that seeded the large-scale structure of the cosmos, to the thermodynamic non-equilibrium that powers every metabolic process, is a necessary condition for the existence of anything capable of recognizing fragility as such. A stable universe is a dead universe. The universe we have is unstable, temporary, running down, balanced on knife edges that could in principle have been otherwise, carrying within itself the seeds of its own eventual dissolution at every scale from the quantum vacuum to the cosmic expansion. And it is, for that reason, rather than despite it, a universe in which stars burn and planets form and chemistry develops and organisms evolve and minds emerge that can stand at the edge of everything and look back across 13.8 billion years of fragile, temporary, improbable complexity and recognize it for what it is. The terrifying truth about how fragile everything in the universe really is turns out, when followed all the way to its conclusion, to be the same truth as the most astonishing fact about the universe. The fragility and the complexity are not in tension. They are the same thing, viewed from different timescales. From the timescale of a human life, the universe looks permanent, and the fragility looks like a threat. From the timescale of physics, the permanence is the illusion, and the fragility is the condition of possibility for everything that makes the universe worth having in the first place. The atoms in your body are stable enough to have lasted since a star died billions of years before the sun formed. They are not stable forever. The laws of physics that govern your chemistry are features of a vacuum configuration that has persisted for 13.8 billion years. They are not guaranteed to persist forever. The star that warms this planet has burned steadily for 4.5 billion years. It will not burn forever. The universe that produced all of this began in a state of extraordinary low entropy and has been consuming that entropy ever since. The account will eventually run to zero. Everything is temporary, everything is fragile, everything is contingent. And because of that, rather than despite it, you are here, in this moment, capable of knowing all of this, which is the most remarkable thing the universe has produced in the entire span of its existence. Subscribe to Nocturnal Space. Turn on notifications. Leave the word fragile in the comments if this reached you tonight, because you are made of atoms that should not exist forever, governed by laws that sit on a knife edge, breathing air on a planet warmed by a temporary star in a universe that is fragile all the way down to its foundations. And that specific combination of fragilities is the only reason you are here to know any of it. The fragility is not the problem. The fragility is the point.